Hello, I'm Norman Wildberger. Today we're going to look at row reduction in its entirety, both the first half that we talked about last time and the second half, which is sometimes called back substitution. Now, row reduction is a very important algorithm in linear algebra. In fact, it's perhaps the most important algorithm. It's used to solve a wide variety of problems in the subject. So we're going to get a sense of that today, and we'll start off by reminding you how the first half of row reduction goes. And then we'll move on to describing the second half, back substitution. So here's a system of equations, a very simple system. Two variables, x and y, two equations that, if we like, can represent two lines in our two-dimensional affine space. We can rewrite this system of equations in matrix form, ax equals b. There's the matrix A of coefficients, our vector of variables, and our right-hand side. Now we form the augmented matrix by combining these two objects into one big matrix with a line separating the left and the right-hand side. And we perform elementary row operations to row reduce this matrix. So what we do first is we use this entry here as a pivot entry to reduce this one here to 0, to eliminate the entry here. And the way we do that is to replace the second row with the second row minus the first row. That's what we write here just to record what we're going to do. So row 2 is going to be replaced with row 2 minus row 1. So we take this row 2 and we subtract row 1. 1 minus 1 is 0. Minus 1 minus 2 is minus 3. And 1 minus 6 is minus 5. Now actually at this stage here, the matrix is already in row echelon form, which means two things. It means that all the rows of zeros are at the bottom of the matrix. In this case there are no zeros, that's all right. And it means that the leading entries of each row, namely this one and this one, are staggered to the right as we move down. All right, now let's carry on a little bit further and go to what's called fully reduced row echelon form. And what that involves is, first of all, trying to make this leading entry a 1. Right now it's a minus 3. We're going to multiply this row by minus 1/3, making that a 1, and making this entry 5/3. Now all our leading entries are 1s. That's a good thing. Right? That's one of the key points of the fully reduced row echelon form, that all the leading entries are now equal to 1. 1 is particularly easy to work with. And now what we're going to do is we're going to go back from the bottom up towards the top. And what we're going to do is we're going to start with this bottom leading entry, the 1, and make everything above it 0. So we're going to use this row and add multiples of this row to all the rows above it, getting rid of all the entries above our leading entry that we're focusing on right now. In this case, there's just one of them. So what are we going to do? We're going to take this row here and we're going to subtract 2 times the row 2. Illustrated here, row 1 is replaced with row 1 minus 2 times row 2. So 1 minus 2 times that, well, that's just 1. 2 minus 2 times 1 is 0, as we've required. And 6 minus 2 times that, well, that's 6 is 18/3 minus 10/3, that will be 8/3. And now it's in what's called fully reduced row echelon form. It's now very easy to read off what the solutions are. The new equations that correspond to this augmented matrix are x plus 0y equals 8/3. In other words, x equals 8/3. And 0x plus 1y equals 5/3. Or in other words, y equals 5/3. So we found a solution to the original system. And in fact, we've already discussed this particular example. I've illustrated this, showing you what these lines look like in an earlier video, and you may recall this solution that we obtained by looking at the inverse of a 2x2 matrix. This is another way of finding the intersection of these two lines. And it's really just glorified high school algebra done in a very systematic and organized fashion. So let's have a look at another example. This time we're considering two parallel lines in the plane. 2x plus y equals 4 and 4x plus 2y equals 3. There's the AX equals B form for the system in matrix form. And here's the augmented matrix for this system. We're going to row reduce this by starting with this pivot entry here and removing everything below it. So we're going to replace row 2 with row 2 minus 2 times row 1. 4 minus 2 times 2 is 0. 2 minus 2 times 1 is 0. And 3 minus 2 times 4 is minus 5. This corresponds to this system of equations. And the second equation is 0x plus 0y equals minus 5. What kind of an equation is that? No matter what x and y are, this could never be true. What does that tell us? It tells us that there's no solution to this system. There are no values x and y that satisfy both these equations, and therefore no values of x and y that satisfy the original equations. And the reason that we've had this problem, well, it's not really a problem, but the reason why we've had no solution is because of this row right here. And it's the fact that this minus 5 is a leading entry. This is the leading entry of this row, and it's actually on the right-hand side of our divider, making the right-hand column a leading column. So a bunch of zeros followed by something non-zero. That's the essential reason why we do not get a solution. Here's a bit more of a complicated example. Let's have a look at 3 equations in 3 variables x, y, and z. There's the augmented matrix for it. And let's row reduce it. So we'll start with this pivot entry and make sure that everything below it is 0. So we have to get rid of this minus 1. Okay, I haven't written down what we're going to do, but I'll tell you. We're going to just take this row here, and we're going to add row 1 to it. So 1 plus minus 1 is 0, 1 plus 2 is 3, minus 1 plus 1 is 0, and 4 plus 2 is 6. Now we look at this same system, but we move our attention to this smaller submatrix below and to the right of the pivot entry we've just been considering. So in this smaller submatrix now, this is the new pivot entry. And our job is to get rid of everything below it, namely to get rid of that 3 there. So we take this row and we're going to subtract 3 times this row from this row. So 3 minus 1 times 3 is 0. 0 minus 3 times 2 is minus 6. And 6 minus 3 times 0 is still 6. Now it's in row echelon form because the 3 leading entries are staggered down to the right. It's not as nice as it could be. We can see that we could simplify it a little bit by taking the minus 6, which is a common factor of this last row, and dividing by it. All right, so we divide this by minus 6. Then the third row becomes simply 0, 0, 1, minus 1. And that's preferable because now all the leading entries are 1. But still, if we wrote down equations for this, well, we could write them right here. They correspond to x plus y minus z equals 4, y plus 2z equals 0, and z equals minus 1. Now, can we read off what the solutions are? We can, by starting with the bottom equation. So that's telling us z equals minus 1. And then once we know what z is, we can plug back into this equation so that y minus 2 equals 0. That means that y must be equal to 2. And once we know that z is equal to minus 1 and y is equal to 2, we can plug both of those values into the first equation and solve for x. So x plus 2 minus minus 1 is 4, and that means that x has to equal 1. And that's why the system is called back substitution, what we're doing now, the second half of row reduction, where we start with one variable, basically the bottom, the one corresponding to the bottom row, that leading entry there. We evaluate what it is, and then we use it to evaluate the second bottom entry or variable, and then use all those to get the variables successively higher. That's called back substitution, and we can also do it in a more systematic way using just the matrices. So what we don't really want to do is this, where we convert this into high school algebra and then do high school algebra that we've just done. We prefer to have a very systematic procedure that only works with the matrices. So our next step is to clarify what we need to do to this matrix to get it into a form where we can read off the solutions without any further calculation. So let's make an important definition. The definition of a fully reduced row echelon matrix, or when a matrix is in fully reduced row echelon form. And that means three things. First of all, it has to be in what we've called row echelon form. So I hope you know what that means by now. Two more things are required. In addition, all the leading entries should be equal to 1. And everything above a leading entry should be 0. Let's have a look at some examples. So in this example here, the leading entries are this element, and this element. They're all equal to 1. And if we look at the elements above each of these leading entries, they're all 0. So this one is in fully reduced row echelon form. Here are the leading entries, here, here, and here. And again, they're all 1, and everything above them is 0. That's also in fully reduced row echelon form. Over here, the leading entries. Well, that's not even in row echelon form because the leading entries are not going down to the right as we move down. And it's also not in fully reduced row echelon form because this value is 2. All the leading entries must be 1. And everything above a leading entry has to be 0 as well, so that's also contradicted. So this is definitely not in fully reduced row echelon form. It's not even in row echelon form. And what about this one? A leading entry, another leading entry. They're all 1s. It's in row echelon form, and the entries above the leading entries are 0. And so now the process of going from a row echelon form to a fully reduced row echelon form, it's called back substitution. And that's what I've already illustrated with some examples. So how do we go from a row echelon form to a fully reduced row echelon form? Well, have a look at this one. It's already got 1s as leading entries. If the leading entries were not 1s, we would have to multiply the rows by some appropriate number to make sure that all the leading entries were 1. Then we start with the lowest row, the bottom leading entry, and we make sure that everything above it is turned into 0 by adding that row or multiples of that row to the other 2 rows. So the row 2 is replaced with row 2 minus 2 times row 3. We subtract 2 times this third row from the second row, ensuring that that entry is going to become a 0. But then this entry also changes because this minus 2 times that will be plus 2. And to get rid of this minus 1, we're just going to add the third row to the first row, giving us 1, 1, 0, 3. And now we go up one step. Instead of the third row, we're now looking at the second row and the second leading entry. And we arrange that everything above it be 0. So we're going to just subtract this row from the first row, giving us 1, 0, 0, 3 minus 2 is 1. And this matrix is in fully reduced row echelon form because it's in row echelon form, because all the leading entries are 1, and because everything above the leading entries is 0. And it makes it easy to read off what the solution is. X equals 1, y equals 2, and z equals minus 1. That's the same answer that we obtained in the previous slide with just high school back substitution. This is the matrix form of that. Here's another example that illustrates that we don't have to be working with an augmented matrix. We can row reduce any old matrix, and the procedure is exactly the same. Here, what we've started with is a matrix whose leading entries are not 1, so we divide this one by 2, and we divide this row by 3, giving us this. Then we start with the lowest leading entry, this one right here, and we arrange that everything above it be 0. So we're going to replace that 4 with a 0. How? By adding a suitable multiple of this row to that row. In other words, minus 4 times this one, we're going to add to that. Or to put it another way, we're going to take this row and we're going to subtract 4 times the second row. Giving us 1, 2, 4 minus 4 times 1 is 0, and minus 1 minus 4 times minus 2 is minus 1 plus 8, that's 7. That then is now in fully reduced row echelon form. A general linear system with many variables and many equations can have a whole multitude of solutions. Generally, we expect that solutions come in families and are described via parameters. And the method of row reduction that we've been describing gives us a very precise way of saying exactly how the parameters arise and exactly how the parameters end up shaping the final solution. Let's illustrate the idea with a very simple case. Perhaps it looks too simple, but it's still illustrative, where we have only one equation in two variables. X plus 2y equals 4, which represents a line in two-dimensional space. So we can think about that as an equation that we'd like to solve. We would like to find all the solutions, x and y, to that equation. That's the same as describing all the points on the line. And you can see that it's natural that we have a one-parameter family of points because it's a line. So the augmented matrix for this very simple system is just a one-rowed matrix, 1, 2, / 4. And it's already in fully reduced row echelon form because there's the leading entry, there's only one, and well, there's nothing above the one, so that is already satisfied. Now it's very useful to divide the columns on the left-hand side of this augmented matrix into two different kinds, into leading columns, which are simply columns that contain a leading entry, and to non-leading columns, which are columns that don't contain a leading entry. And since each column corresponds to a variable in the original system, we can also divide the variables into those that correspond to leading columns and those that correspond to non-leading columns. And what we're going to do here is we're going to set the y, the one that corresponds to a non-leading column, equal to a parameter. And we'll say the parameter is lambda. So suppose that we set y equals to lambda. The idea is that that's free, that we can let y be any value that we want. Well, then the equation that's represented here is x plus 2 lambda equals 4 because we've replaced y with lambda. And we can solve that directly to get x equals 4 minus 2 lambda. So the possibilities for the pair x, y in terms of lambda are that x is 4 minus 2 lambda and y is lambda, and that's a description of all the points lying on that line. So every point on this line is of the form 4 minus 2 lambda for some value of lambda. For example, if lambda is 0, then we would get the point 4, 0. If lambda was 1, we would get the point 2, 1. If lambda was minus 1, we would get the point 6, minus 1. Those are all points lying on this line, and every point on the line is of this form. So this is a parametric solution to this very simple system of equations. Let's look at a slightly more complicated example. In this example, we have one equation with three variables, representing a plane in 3 dimensions. 3 dimensions x, y, z. One linear equation is a plane. So when we're solving this equation, what we're trying to do is we're trying to describe all the points which lie on this plane. And intuitively, we can recognize that this is going to be a 2-parameter family of points, because there's essentially 2 directions to go on the plane. We can get that by looking first at the augmented matrix, which is again in fully reduced row echelon form, so there's nothing to do with that. And on the left-hand side, the columns are separated into the leading column, which is only the one corresponding to x. And now there are two non-leading columns corresponding to the variables y and z. And what we do is we set each of these non-leading variables equal to a parameter, a free parameter that's allowed to be anything it wants to be. So we'll set y equal to, say, lambda, and z equals, say, mu. Now this one equation then reads x minus lambda plus 3 mu equals 5, allowing us to solve for x in terms of mu and lambda. So x is 5 plus lambda minus 3 mu, y is lambda, and z is mu. So in terms of these two parameters that we've introduced, the general point lying on the plane has this form. For any value of lambda, for any value of mu, this is a point on the plane. And every point on the plane is exactly of this form, for some lambda and mu. Now the meaning of the things in here is clarified by separating this out and peeling off the ingredients that don't depend on lambda, namely the constant 5 and just 0 and 0. We'll peel that off separately. And then we'll write plus lambda times something. So lambda times 1, 1, 0, that vector, plus mu times something, the vector minus 3, 0, 1. So when we write it like this, we recognize this is a parametric form for a plane. It's the plane that goes through this point and has these two vectors as its direction vectors. So we're allowed to start at this point and go any multiple of 1, 1, 0 and any multiple of minus 3, 0, 1, and that will get us to any point on the plane. So that geometric description comes around from the parametric form for the solution, which comes about by setting the non-leading columns equal to parameters and solving for the leading column variable. Those last two examples were pretty simple. Now let's have a look at a slightly more complicated situation that shows how these parameters get introduced in the course of things. We're going to start with two equations in 3 variables. Each of the equations represents a plane in 3-dimensional space. So we have these two planes in 3-dimensional space, and we're interested in the intersection between those two planes in describing the common solutions to the two equations. Geometrically, it should be a line. That is, if the planes are sort of in general position. So to solve the system, we convert the two equations into an augmented matrix. We row reduce. We use this as a pivot and subtract 3 times the first row from the second. Then we look at this minus 1 here, change it to a plus 1 by multiplying that second row by minus 1. Now the two leading entries are both 1s. And now we're going to get rid of that 2 above the 1 by subtracting 2 times this second row from the first row, giving us this here. Alright, so it's now in fully reduced row echelon form. And I've circled the leading entries, or the pivot entries. And the columns containing those entries are called leading columns. So there are 2 leading columns in this fully reduced row echelon form. And on the left-hand side, there's also one other column. We could say that's a non-leading column. It's the non-leading column that is responsible for the parameter in the solution. In other words, since the variables are x, y, and z, it's the third variable z which corresponds to a parameter. So we set z equals to lambda. And then, solving the first equation for x, x plus 17z equals 18. So x equals 18 minus 17z, or minus 17 lambda. And the second equation is y minus 10z equals minus 10. So y equals minus 10 plus 10z, or plus 10 lambda. So that's a complete solution for x, for y, for z, all in terms of this free variable lambda, which can be anything it wants. So we put it all together in a vector, x, y, z, put the three things together, and we get a description of the common solutions to this system. Any point x, y, z which lies on here has this form for some value of lambda. And again, it's a little bit clarified geometrically if we separate out the entries that depend on lambda and the ones that don't. The ones that don't depend on lambda are 18, minus 10, and 0. And then there's plus lambda times minus 17, 10, 1. And in this form, the geometry is clear. This is a line through this point with this as a direction vector. So we're allowed to start here and add any multiple of this vector, either positive or negative, and we're getting a line through this point with that as direction. And that's a description of the common solution to these two planes. So we've solved the system. Now it's good if this algorithm is not just something that you memorize, but something that you understand why it works. So let's explain, why does this method actually work? This idea of introducing parameters for some of the variables and not for the others. So let's have a look at a little bit more complicated system. Suppose that we have a set of, say, 1, 2, 3, 4 equations in 1, 2, 3, 4, 5, 6 variables, say x1 up to x6. And suppose that the original system, which we don't know, eventually is row reduced to this fully reduced row echelon form. So now there's a leading entry in the second, fourth, and sixth columns. Those would be called the leading columns. So the leading variables are x2, x4, and x6. And if we think of the corresponding equations, here they are right here. So I've just gone from the matrix to the equations. The first one is x2 plus 2x3 plus 3x5 equals 5. The next one is x4 minus 2x5 equals 4. And the last one, x6 equals 3. And the thing to observe about this system is that each of the leading variables, x2, x4, and x6, appears exactly once in this entire array. And that's simply a reflection of the fact that in each one of these columns, there's only one place where there's not a 0, namely at the leading entry. Because we've arranged that all the other elements in that column are 0. We've arranged that all of them below were 0 when we first row reduced, and we arranged that everything above them was 0 when we did our back substitution. That's why x2, x4, and x6 appear only in these spots. One of them for each one of these equations. So the non-leading variables, the ones corresponding to the non-leading columns, namely x1, x3, and x5, are appearing here, and actually x1 doesn't even appear. Those variables can be anything they want, and we can still solve for x2, x4, and x6. In other words, it doesn't matter what these values are. It doesn't matter what this value is, and it doesn't matter what x1 is. We can still figure out what x2 is, what x4 is, and x6 is. And that's why we have that freedom in essentially replacing the variables with parameters, because there's nothing to stop them from being anything that they want to be. We still can get a solution. So in this case, we could set x1 equal to lambda 1, x3 equal to lambda 2, x5 equals to lambda 3. 3 parameters. And then these 3 equations would allow us to solve for x2, x4, and x6 in terms of these 3 parameters. Now it so happens that x6, okay, it's just equal to 3. It has essentially plus 0 combination of lambda 2, lambda 3, and so on. That's fine. But altogether then, these 6 equations represent a complete description of the solution to the original system. x1 is any parameter lambda 1, x3 can be any parameter lambda 2, x5 can be any parameter lambda 3, and x2, x4, and x6 are determined by these equations. And that describes the entire solution set. So now that we have this fundamental algorithm down, the algorithm of row reduction or Gaussian elimination, it's time to use it to solve some explicit problems. The first problem I'm going to have a look at is this one, that we are working in three-dimensional space and we have a vector v, minus 5, 7, and 10. And we're interested in the question, can we write this vector as a linear combination of these 3 vectors? In other words, something times this one, plus something times this one, plus something times this one. We want to know, can we do that? And if so, how? So here's the relevant equation. It's a vector equation. We're saying x1 times the vector 3, 1, 2, plus some x2 times the vector 1, 3, 5, plus x3 times the vector 0, 2, 4. It's a general linear combination of those 3 vectors. We're saying it equal to the vector v. We want to know, can we solve this single equation? It's an equation for x1, x2, and x3. Well, if we look at the first components of those vectors, we get the equation 3x1 plus x2 plus 0x3 equals minus 5. That's a single equation. And the second component gives us a second equation, and the third component gives us a third equation. So this single vector equation is really completely equivalent to these 3 linear equations. Well, we're usually talking about a system of linear equations in x1, x2, and x3. The augmented matrix is this one here. And this illustrates, I think, an interesting and important point. That a system represented by an augmented matrix like this can be thought of in at least a couple of different ways. Very different ways. For example, this augmented matrix is the matrix for this linear system, which we can think of as representing 3 planes in 3-dimensional space. On the other hand, the same matrix is representing this single vector equation, which has a completely different geometrical content, asking whether one vector can be written as a linear combination of 3 other ones. 2 different problems, the same augmented matrix results. So let's apply row reduction, let's apply this Gaussian elimination together with back substitution and see if there is a solution, if the solution is unique or not. Maybe there's a parameter involved. We don't know until we've row reduced the matrix. Alright, it would probably be a pretty good idea for you to go away and apply row reduction to this matrix and then come back and see if what you get agrees with what I've got. So we start with the matrix, and our first job is to eliminate everything below the top leading entry. Now the top leading entries here are 3, and that would require me to take 1/3 of this row and subtract it, or multiples of it, from these other rows, and I'm a little bit lazy. I prefer to work with natural numbers or integers rather than fractions. So I'm going to do something which I don't have to do, but just makes it a little bit easier for me in this case. I'm going to swap these 2 rows. The only reason I'm going to do that is so that there's a 1 up in this leading entry position. It's nice to have 1s in the leading entries. And I'm just going to arrange it this way. There's a bit of flexibility in the system. You can make things easier for yourself with little tricks like that. Now I'm going to take this row and I'm going to subtract 3 times it from row 2, and I'm going to subtract 2 times it from row number 3. So just to show you, so this thing here minus 3 times that. So 3 minus 3 times 1 is 0. 1 minus 3 times 3 is minus 8. 0 minus 3 times 2 is minus 6. And minus 5 minus 3 times 7 is minus 26. This third row minus 2 times the first row. 2 minus 2 times 1 is 0. 5 minus 2 times 3 is minus 1. 4 minus 2 times 2 is 0. 10 minus 2 times 7 is minus 4. Okay, now I'm going to do a similar kind of thing. I'm going to now look at this smaller submatrix obtained by moving down and to the right of the pivot entry we've just worked with. So we're looking at this submatrix now, and I see, well, there's a minus 1 down there. It would be nice if that minus 1 was up here and if it was a plus 1 instead. So I'm going to kill two birds with one stone. I'm going to swap these two rows, and so that's why there's this minus 1, 0, minus 4 becomes up here, but it's not exactly the same. I've swapped it. I've also multiplied by minus 1 at the same time. So I've combined two operations at one go. And this second row is now in the third position. It looks a little bit different. What have I done? I've done something else to it. I've simplified it a little bit. I've divided by 2, and I've also multiplied by minus 1. Those are both allowable operations, and I've done them sort of all at the same time. That's how I've gone from here to here. I've swapped rows 2 and 3 and multiplied this row by minus 1 and this one by minus a half. Now I'm in a position to use this pivot entry here to get rid of the 4 beneath it. So I'm going to take this row and subtract 4 times this row, giving me this. It's now in row echelon form. And now I'm going to move towards getting it in fully reduced row echelon form by, first of all, dividing the third row by 3 so that all the leading entries are 1. Now all the leading entries are 1. And now what's the next step? When we back substitute, once we've all got all our leading entries 1, we have to get rid of all the things above the leading entries. So we have to work from the bottom and add multiples of the rows at the bottom to the rows on top of them to get rid of everything above the leading entries. So I'm going to use this third row to get rid of this 2. I'm going to take this row and subtract 2 times it from this row here, giving me 1, 3, 0, 9, and these 2 rows don't change. Now I move up 1. I'm now looking at this leading entry. I want to clear everything above it. I work systematically. So we take this row here and we subtract 3 times this row here. 1 minus 0, 3 minus 3, 0 minus 0, 9 minus 12 is minus 3. And now we can read off the solutions. The first equation reads x1 equals minus 3. The second equation reads x2 equals 4. And the third, x3 equals minus 1. There are no parameters. There's a unique solution. x1 has to be this, x2 has to be this, x3 has to be this. And we could have seen that there was going to be a unique solution actually quite a long time ago. Even right up at this level here, we could recognize that each of these columns was going to be a leading column. So even at this stage, we could have predicted that there was going to be a unique solution. No parameters, because there are no non-leading columns on the left-hand side. Our second problem has the same general format. We are asking, can we write this vector in the plane, vector v equals 5, 3, as a linear combination of these 3 vectors, v1, v2, and v3. It's a bit easier to visualize now because we can draw a 2-dimensional picture. Let me remind you how you do that. You set up coordinate axes in rather a general fashion. It doesn't really matter what the coordinate axes look like. So I've chosen the E1 axis in this direction, the E2 axis in this direction, and equal spacings here and here. It's not a rectangular grid though, and it's not important that it be. Now with respect to this basis E1 and E2, our first vector v is 5, 3. So it's 1, 2, 3, 4, 5 in that direction, 3 up, so it's that vector there. And the 3 vectors v1, v2, and v3, there's 1, minus 1, 2, 1, there's v2, and minus 1, 4, that's minus 1, 4, there's v3. So the question is asking, can we express this vector v as a linear combination of these 3 vectors? Well, it's pretty obvious geometrically that you can do this. For example, I could say, well, we're just going to go in this direction. Say we're going to do a couple of multiples of v2, maybe up to about there, maybe about, a little bit, maybe less than 3 times v2 out there. and then we'll subtract a little multiple of v1, and that will express v as a linear combination of v2 and v1. But there's other ways of doing that. You could also express it in terms of v2 and v3, or in terms of v1 and v3, or perhaps in terms of all three of them. So geometrically, we're already thinking there's probably more than one solution here. And we'll see that there is. And the algebra tells us that without any picture necessary. So even if we don't have any visualization, just stick with the algebra, we get the right answer. There's a system we're interested in. We're interested in expressing 5, 3 as a linear combination of these three vectors. There's the corresponding two equations obtained by looking at the first entry and the second entry. And here's the augmented matrix for either this or this. We now have to row reduce that augmented matrix. Please go ahead and do it. Alright, so the steps are pretty familiar now. I'll go a little bit quicker. We're going to row reduce. We're going to use this pivot entry to get rid of the -1. Then we're going to take this leading entry and make it 1 by dividing this by 3. We get a fraction 8/3 on the other side. Then we're going to use this entry here to get rid of the 2 above it by adding a multiple of this row, actually subtracting twice this row from the top row. And we get this fully reduced row echelon form. On the left-hand side, there are two leading columns, the ones containing the leading entries. And there's one non-leading column. So there's going to be a one-parameter family of solutions in the answer corresponding to that non-leading column. And in fact, that non-leading variable, x3, is the one that we're going to set equal to the parameter. So x3 is equal to lambda. Then we solve for x1 using this equation. We solve for x2 using this equation. We put all three answers together in a vector. We get x1 equals -1/3 plus 3 lambda. x2 equals 8/3 minus lambda. x3 equals lambda. We get a one-parameter family of solutions corresponding to our intuition. In particular, if, say, lambda is equal to 0, then we see that x1 is -1/3, and x2 is equal to 8/3, and x3 is equal to 0. If you go back to the picture that we had on the previous page, that corresponds to using almost 3 multiples of x2 and -1/3 multiple of x1 to combine v1 and v2 to get v3. Different values of lambda correspond to different combinations of these three original vectors to create the vector 5, 3. So a very important algorithm, the backbone of linear algebra. And although the examples that I've been looking at have been pretty modest in size, the idea is to do it systematically so that we can understand what happens even if the system is very large. If we have hundreds of equations in hundreds of variables, say. And that kind of thing does come up in practice. That's why we're proceeding very systematically and coherently. Time for some exercises to give you a chance to practice this very important tool. And it's important that you actually do it, get used to it, become familiar with especially the subtlety of how many parameters there are, whether there's solutions, whether there's unique solutions, whether there's parameters involved in the families of solutions. Let's have a look at some exercises. Alright, so for our first exercise, I'm asking you to find all solutions to various systems. Here's an AX equals B system in matrix form. Here are 2 equations and 3 variables. Here we're looking to see how many ways we can write this vector as a linear combination of these 3 vectors. Here's another little system, a little bit symmetrical, interesting, the left-hand side. Here we have a system much like this one here, except that the variables are not x1, x2, x3. They happen to be a, b, and c. Our variables don't always have to be x's and y's. Here's another system a little bit like this one, except with some minus signs between the 2 variables. So I want to know, are there solutions? Is there a unique solution? If there are many solutions, how do you describe all the solutions via parameters? In this question, we're also trying to solve a system, but there's a little bit of a twist. Okay, I've included an extra unknown, mystery unknown A. And I'm asking the question, for which values of A do the following have a unique solution, no solution, or an infinite number of solutions? So for example, this system here, you should think of it as a usual system in X and Y. It's just that this particular value perhaps has been rubbed off. You don't know what it was. Maybe it was a 4 originally, maybe it was a -3. Let's say it's been rubbed off and you don't know what it is. So what happens when you try to solve the system? The answer that you get probably depends on, perhaps, on what that number actually is. So I want you to tell me, for which values of A do you get a unique solution? For which values of A do you get no solution at all? For which values of A do you get an infinite number of solutions? Say some parameters. And here the same kind of thing, a little bit more complicated. 3 variables, 3 equations, and a mystery A appearing there. Same kind of thing over here. And here a slight variant. Here the A occurs not on the right hand side but right there as a coefficient. So we have a mystery coefficient that we don't know, and we want to know how does the system depend on the value of that particular coefficient. Still row reduction, it's just that there's a little bit of variability in the row reduction or in the augmented matrix. Instead of having all numbers, there will be an A sitting someplace. You have to deal with that A just as if it were a number. And for our last question, we're going to go back right to the fundamental question of linear algebra that we started with. When we have one set of variables connected linearly to another set of variables, and we want to invert the relationship. So we want to solve for the x's in terms of the y's. Now you already know how to do this using the idea of an inverse matrix. But now we have another possibility. We can row reduce this system, treating y1 and y2 as numbers that we happen not to know the exact values of. Since the row reduction technique really only depends on what's happening on the left-hand side, it's the left-hand side that's determining the decisions that you make, the actual process of row reduction is not appreciably different if there's variables on the right-hand side. Except the algebra is a little bit more complicated, but the ideas are really exactly the same. So I want you to solve this system using row reduction. In fact, I want you to solve all of these systems using row reduction, and I want you to compare this with the inverse matrix method. So some of these will perhaps be familiar that we've done them already previously. And in this question here, I've got variables u1 and u2 and t1 and t2 instead of the usual x's and y's, just to get you used to the idea that variables are not always just x's and y's. So with this very practical tool now at our disposal, and you've had lots of practice, hopefully, with these problems, it's time now to look for a lot of different applications of row reduction, Gaussian elimination. So next time we're going to do that, we're going to look at lots of different applications, including the problem that actually got us started in this direction, which was finding eigenvectors for matrices. So we're going to show you how to do that, and many other things also next time. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.